So, good morning, everybody. It's really amazing to see so many of you that early in the morning. Thank you very much for coming. I take it you're as excited about causal inference in the brain as I am. So, my name is Moritz Grosse-Wentrup. I'm at the Max Planck Institute for Intelligent Systems in Tübingen, Germany, and I have the pleasure of introducing the first symposium today. So, I take it that we are all interested in the brain, and that we all agree that the brain receives stimuli and translates these stimuli into behaviors. At the same time, I think we all agree that the brain is not this unstructured mess, but that it gives rise to certain cognitive components like perception, planning, and action. And if we're cognitive neuroscientists, we maybe even believe that these cognitive components are also sufficient to describe how stimuli are translated into behaviors. Now, the big problem is I've used causal terminology to describe all this. So the brain processes stimuli, generates behavior. It gives rise, neuroactivity gives rise to perception, planning, and action. Yet at the same time, all those tools that we have or that we currently use to study these relations are merely associational. And that's a big problem. And those methods that are currently mostly used to study causality, like Granger causality and dynamic causal modeling, it's mostly about causal relations within the brain, not causal relations between the brain and the outside world. In our symposium today, we want to chart the current state of the art in really making inferences about how the brain gives rise to cognitive components to behavior. And we will do this by first starting with a talk by Poldrack on what it actually is that we're mapping onto the brain. What are the cognitive components that we're interested in? Then Martin Lindquist will talk about the various causal frameworks, the causal languages that we have available, and why it is so hard to move from observational, correlational studies to causal statements. Then Sebastian Weichwald will talk about how actually interpreting those associational encoding, decoding models that we currently widely use, how interpreting these models is actually a form of causal inference, and about the assumptions that you need to be aware of when doing this, and the results that are supported or not supported by empirical evidence. And in the end, Christoph Herrmann will tell us how actually causal hypotheses that can be generated from purely observational data can be tested by electrical stimulation of the brain. So we will have 15 minutes for each talk. There will be no discussion or questions after each talk, but a joint discussion at the end of the symposium. So thank you again for coming, and Russ, let's welcome Russ Poldrack.
Well, good morning, everyone. Clearly, the party didn't go late enough last night. Cool. So I'm going to sort of be on the ontology side of things today, thinking about what is it that we're trying to map onto the brain. And I want to start with a 8 a.m. thought experiment. You're all chemists, okay? And there's questions you would expect chemists to be able to answer, like, what are all the enzymes, right? Hopefully chemists could tell you what are all the enzymes. And in fact, if you want to know the answer to that question, there's a set of books called The Enzymes, where you can go and see what are all the enzymes. It's like 40 volumes now. And in fact, you can also go to the gene ontology and see not just what are the enzymes, but where do they sit in, different sort of biological pathways, what do they do, right? So you might hope that psychologists would be able to answer sort of the analysis question, what are all the psychological functions? What are the things that minds do? And you might hope that if you went to a cognitive psychology textbook, for example, that it would give you that answer, but unfortunately it kind of doesn't. It might talk about sort of the very large, things like memory and attention and language, but there's nowhere in these books that sort of says these are all the things that minds do. And ultimately that's what we want to sort of map onto the brain. And so we, about 10 years ago, started developing a project called the Cognitive Atlas, which is basically an attempt to write down all the things that minds do and all the ways that we measure them and sort of the relationships between those things. So it's available at cognitiveatlas.org, and it's an open project, so anybody who's interested can go on and actually sign up to contribute, and hopefully some of you will be inspired to do that after today. But the idea is that basically we want to sort of first distinguish between two sort of grand classes of things, what we call mental concepts. These are the sort of latent psychological things that psychologists are interested in, but we can't see, right? These are things like executive function and working memory and response inhibition. And the only way we can get at those is by measurement, right? So we have tasks that we have people do, and we think that those tasks measure things going on in the head. So one of the sort of important distinctions here is really being clear about what's a cognitive construct and what's a task. So, for example, we shy away from using terms like working memory task, because that's basically a theory about what the task is measuring. So we try to say, this is a task that is described in terms of what it does, and then we say this particular task, can't do that. This particular task measures some particular set of psychological constructs. And that's the knowledge that we want to then go on to use to try to understand mappings ultimately between brain activity and psychological constructs. So let's say you're interested in working memory. You would put working memory into the search field, and you get back a list of concepts related to working memory, and you go to the working memory page, and you see it tells you things like what are all the different kinds of working memory, like spatial working memory and semantic working memory. What are the parts of working memory, things like updating or interference resolution. And it'll also tell you what are all the ways that we know how to measure working memory, all the different tasks that we might use to measure working memory. And on each of those tasks, we lay out what's the particular measurement, because tasks often measure lots of different things. What's the particular contrast or measurement on that task that is related to this particular construct? Then we have separately for each task a page. So, for example, here's a page for the operation span task that tells you what do we think it measures, what are the different conditions and contrasts, what are the indicators, the things that are actually being measured, like accuracy or reaction time. So we have descriptions for each of the tasks that tell you all these things. We also sort of try to aggregate things into larger, what we call collections. There's really two kinds of these. One is what we call a task battery. And this is the idea that, there are these things like the Wechsler Adult Intelligence Scale, which are sort of collections of different tasks. So this might have, 10 different tasks. And then there are sort of measurements that are derived from those. And then we also have come up with a way to sort of describe theories. The idea is, what is a theory? A theory is a set of sort of claims about relationships between things. So, for example, you can define Baddeley's model of working memory as making claims like phonological loop is a kind of rehearsal loop, phonological loop is a part of auditory working memory, and so on. And so that's how we would define a theory. So currently there's about 800 mental constructs, 700 tasks. We have a web API, so you can actually automatically grab the information, and a Python package that's available on PyPy if you're interested to let you sort of automatically deal with the ontology. So what can we do with it? I want to talk about two different ways that we can think about using it. And the first is sort of subversive, which is basically trying to ask, has psychology actually made much conceptual progress since 1890, right? So many of you might be familiar with William James's Principles of Psychology, probably the best psychology book ever written. I recommend going and reading. It's available free online. So we, and this is something that was published on my blog recently, I went through and basically took all the cognitive atlas terms and looked at how many of them show up in this psychology book from 1890. And it turns out about a quarter of them do. And what's interesting is if you look at those, these are examples, they all sound like things that we could be studying here today. And in fact, if you look at the topic headings in William James's book, most of them, other than the language in which they're written, sound like things that people could be studying today. So I wanted to compare this to biology, right? It's pretty clear that biology has had a conceptual revolution, right? People really changed the way they think about biological things since 1890 and today. And we can quantify that by looking at the language that people use. So the gene ontology gives us basically all the terms of biology, of sort of modern biology. And so we can quantify I found a couple of books, biology textbooks from the 1890s, one by Huxley, one by Parker, and looked at how often these gene ontology terms show up in those books. And the answer is much less frequently than what we see with the Cognitive Atlas in William James. In fact, none of the molecular function terms show up because molecular biology didn't exist in 1890. But clearly, this is what a conceptual revolution looks like. People just don't use the same words, right? Whereas many of the words that we use are sort of historically old. Another way to look at this sort of more broadly is with this thing called the Google Ngrams corpus, which basically Google's gone through on about 3.4 million books and said, how often does each set of 1, 2, 3, 4, 5 words show up in every year across those texts? So you can quantify kind of the presence of Ngrams over time. And so I did this as well, starting at 1800, coming up to today. And what you see is that psychological concepts are pretty linguistically ancient, right? So for the concepts that are a single word, about 80% of them were present in our lexicon in 1800. And even the 2- and 3-word phrases, you see that they were fairly prevalent, certainly by 1950. Whereas if you look at the gene ontology, you see that, particularly for the molecular function, but even for cellular components, things like endoplasmic reticulum and Golgi apparatus that you would think have been around for a while, most of those were not in use until relatively recently. So this suggests that psychology has a ways to go compared to other sciences in kind of bringing its ontology up to sort of beyond a pre-scientific understanding of the mind, or at least that's a hypothesis that this generates. Now, the question is, how do we go about trying to sort of test and improve the ontology? And one of the ultimate goals that we've had is to be able to do sort of ontology-driven meta-analysis so we can ask, which parts of the ontology are right, which parts are wrong. And so we've recently come up with an approach to doing this where we basically take data that have been generated from a particular task, and these are going to be data from the NeuroVault project, which basically is a project for the sharing of statistical maps. So in this case, we took 93 different tasks, and we went through and annotated them, which basically involves for each task going in and saying, what do we think this particular contrast on this task measures in terms of psychological function? So in some sense, it's like going in and reinterpreting each one of these 93 papers. It's actually quite labor intensive. It took us many hours of sort of thinking through these different tasks and arguing about them. But ultimately, we have an annotation so that for each thing we say, this particular contrast measures risk and reward anticipation and response execution. And now what we can do is span directly via that task label from data to cognitive concepts. And we can start doing a full ontological meta-analysis. So the first thing we can ask is basically, how does the similarity of the images that are evoked in the imaging study related to the similarity of the ontologies or the ontology mapping of those different data sets? So what we can do is for example, you have one task on the left that, for example, is a visual sentence recognition task, and then what we can do is kind of propagate up in the ontology and give a little bit of weight to the parents of each of the concepts that we think is engaged. And then compare the two ontologies using tools that come from the gene ontology analysis world. So we get a similarity between the ontologies and then just the Pearson correlation between the images, and we can say, how well do these overlap? If the ontology is really capturing something about, if it's reflective of the underlying neural processes, we should see a relationship, and indeed we do. It's not perfect, obviously. There's a lot of reasons why it could go wrong, but we're capturing about a quarter of the variance in the image similarity by that ontological similarity measurement. Now we can further go and ask, and this is sort of one of the holy grails for us has been to be able to say, given some set of cognitive processes, can we predict what the imaging data should look like? And so we've started doing this using a voxel-wise encoding model. So the idea is we take those 93 data sets from NeuroVault that have been annotated using the Cognitive Atlas, and then we fit a model at every voxel where we say, that we're modeling the response at that voxel to each of those tasks. And then the design matrix is basically the cognitive ontology encoding for each of those 93 tasks. And in this case, what we do is we basically just propagate up the ontology. So we say if anything is turned on, it's like if working memory maintenance is turned on, and that's a part of working memory, we just basically give full weight to all of the parents. So whereas in the previous analysis, the weight kind of died off as you go up the ontology, in this case, we give full weight because we find that actually works substantially better. So we fit a model at every voxel. Because it's wider than it is tall, we have to use regularization. In this case, we used elastic net to give a little bit of sparsity. And then the nice thing about this is it gives you a forward model to then generate the data for any new mapping, as long as it overlaps to some degree with the cognitive processes we've seen before, we can generate the predicted brain image. So we use a trick that Tom Mitchell developed a while ago called a leave two out procedure, where the idea is you fit the model on 91 of the 93 data sets, and then you predict the images for the other two, and then you compare those to the actual images for those two tasks. And if each of those is more similar, just in terms of its Pearson correlation, to its actual data set than to the opposite, then we say that we've successfully predicted the image. And we get 80-something% correct, which is substantially better than a null model, suggesting that we are actually capturing, to some degree, some useful things in this ontology. Now, the thing that really shows that the ontology is what's driving this is if you don't do that expansion, right? If you don't turn on the parents, but you just turn on the specific concepts that we think are engaged on that task, we only get 56% correct, which is kind of barely above chance. And so this is some evidence that using the ontology can actually help you substantially better predict what brain maps should look like. Now, we can also ask sort of how accurate are we for different concepts. So what we do is we take, for each of these different concepts, we take all the concepts that have at least 10 images associated with them, and we say how accurate were we across all the images that included that concept. And you can see that it varies quite a bit from things like response execution or visual object recognition, we actually do really well on. We can almost always correctly predict which image has those. But some we do pretty badly on, like cognitive control. Even though we have 27 data sets that involve cognitive control, so we have a decent amount of data to train on, but nonetheless we don't do very well at predicting the presence of cognitive control. That might suggest that this is not a well-formed cognitive concept, then we need to rethink sort of the fact that we're labeling tasks with this concept. So ultimately, the hope is that if we have multiple ontologies, we can actually use them to test which one sort of better fits the imaging data. So you might imagine you have one model that says these two things rely on different constructs, and importantly, that predicts a particular covariance structure. You might have another model that says it's all one thing that predicts a different covariance structure, and you can compare those to add to the actual data to ask, and this could be behavioral data, it could be imaging data, genetics, whatever kind of data you have that's relevant, and you ask, which one better fits the data, and ultimately you can sort of figure out what's the right ontology. So finally, this is supposed to be about sort of ontologies and causation, and so going back to Moritz's, sort of figure about sort of what is the causal status of mental entities. And I guess the way that I think about this is, ultimately it's neural computations that are implementing all the things that we refer to as psychological functions. The way I think about mental functions is as basically sort of descriptions of equivalence classes of neural computations, right? So the idea is that we use the term working memory to describe a set of different kinds of things that neurons are doing. And in the same way that, you ultimately a mountain and a river all are just, quarks and other subatomic particles, but those are, a mountain is an interesting thing to talk about and a river is an interesting thing to talk about because of their sort of, higher order properties. I think of mental functions in sort of the same way, and I think that they're ultimately, even though we can cache them out in terms of neural computation, they're useful functions to think about. So finally, I just want to thank my collaborators, and thank you.
Oh, there. Oh, thank you. It's a little bright up here. Is it possible to turn that down? Hi. Title of my talk is Establishing Causal Relationships in Neuroimaging. And so it's really clear that neuroscientists are increasingly interested in using data, neuroimaging data, to make causal statements about brain function. After all, there's a lot of people here today. And so in practice, a lot of people are modeling association, using methods that model associations among variables in order to make causal inference, with the associations taken to evidence causation. However, in practice, there's rarely, if ever, any statement about what notion of causation, if any, they're using. And this is problematic in many ways. So what do I suggest that one does? Well, I think that when you're studying causation and trying to make causal claims from the data, it's important for researchers to try to consider what they mean by causation, and I'll get to that in a second. Secondly, it's really important that if you're interested in trying to estimate a causal effect, that you actually define what that causal effect is. And third, I think it's important that once you've done this, to then be able to determine under what circumstances these effects can be estimated from the data. And I'll try to illustrate all these concepts as we move along. So let's start with the first one. Consider what's meant by causation. That sounds like a trivial question, but if you look at the literature, it's not really that clear, because some people are talking about causation seem to mean one thing, while other people seem to be talking about another thing. And that makes things very confusing. And so there's been a lot of different sort of ways of speaking about causation through history, and it goes back way back, but if we go back to, say, Hume in the 1700s, he talked about a kind of deterministic causation. So he said that, well, Z causes Y if Z is before Y, Z is near Y, so in close proximity, and then the last one is that if Z happens, Y always happens. Okay? So he illustrated this using some billiard balls hitting each other and whatnot. However, if you think about this, it's not that strong of a notion, because if you think of something like, cigarettes cause lung cancer, that's something that we, throw out pretty often. It wouldn't be true under this concept of causality, because the last thing isn't true. Even if some people smoke and don't get lung cancer. So obviously, it's not, if you smoke, you don't always get lung cancer. So under this deterministic causation, that wouldn't be a true statement. So maybe this is not what we want to do in this case. And so this led people to start talking about things like probabilistic causation. And this is sort of akin to, Granger causation and whatnot. So you have this temporal priority. So Z causes Y if Z happens before Y. So you have this temporal priority. But then if Z happens, it increases the probability of Y. And so that works with the smoking example, right? Because if you smoke, you're not guaranteed to get lung cancer, but you increase the probability of getting lung cancer, right? But you can work on counterexamples of this as well. So here's one that I like, is that, well, you know what, if the barometer goes up one day, a storm is going to happen in a few hours, right? So did the barometer going up, cause the storm? No, there's some outside factor that's causing, both things to happen, right? So that's a bit of a shortcoming of probabilistic causation. Now, the type of causation that most statisticians, which I'm a statistician, and computer scientists use is one that's sometimes called counterfactual causation. So in counterfactual causation, we say that if Z had not occurred, then Y would not have occurred. Okay, so let's sort of unpack this a little bit. So this poor guy, Bob, he's sick, and he takes medicine and he gets better. So that's good. So the question we want to do, or the FDA would want to know, is did the medicine cause Bob to get better? I mean, that's what we want to do, to know whether or not this was an efficient medicine. Well, in order to answer that question, we really need to know what would have happened if Bob didn't take the medicine, right? Two things could have happened. A, he would have not have gotten better, so he would have stayed ill. Or B, he would have gotten better regardless. Okay, those are two possible things that could have happened. So according to A, taking the medicine caused Bob to get better, because if he had not taken it, he wouldn't have gotten better, right? So in situation A, the medicine caused him to get better. In B, it didn't matter. He got better regardless, right? So the medicine, he could have taken a sugar pill and he would have gotten better, right? Because that's just the way it happened. So in one situation, we have a causation, and in the other, we don't. And so in order to do this, we have to look at sort of this counterfactual thing and compare what happened when Bob took this medicine with the hypothetical situation of what would have happened if he hadn't taken the medicine. And that's how we think about causation a lot in statistics and in computer science. And the mechanism for studying this and conceptualizing this is different. Some people like to use graphical models, sort of the Judea-Pearl type school, and some people like to use something called potential outcomes notation, and that's what we use in statistics most often. So I'll talk about that since I'm a statistician. So counterfactual ideas, such as the one with Bob here, they can be expressed mathematically using this notation. And so it takes a little bit of getting used to. But let's say that you have each individual in the population are in a study, and you can be exposed to 2 different treatments. You guys get a placebo, and you guys get the drug, or something like that. So in this case, each individual has a potential outcome under each treatment. So if I took Russ, I could have either given him the treatment, or I could have given him the placebo. Had I given him the placebo, I would observe y of 0, because that's 0 is the code for placebo. Had I given him the drug, I would have observed y of 1. And that's his outcome under the drug. So those are 2 possible things. In 2 parallel worlds, I could have, in one case, given him the drug, and then I would observe y0, and in the other, I would have given him the placebo and y1, or vice versa, right? And so really what we're interested in is computing what's called unit-level causal effects. So we want to see, well, what's the difference between his outcome had he taken the drug versus had he not taken the drug? The problem here is it's a missing data problem, because he either takes the drug or he doesn't. So I can't actually estimate this in practice. So instead what we need to do is we need to focus on introducing sort of defendable assumptions that we can use to estimate this from the data. Okay? So here's another example. We have an experiment, 6 subjects. 3 people get the drug, 3 people get a control, and we measure an outcome for each subject. Okay? We want to see whether or not the treatment has any effect on the outcome. Okay? So here's the little math notation. So z is equal to 1 if you're in the treatment group. Z is equal to 0 if you're in the control group. Y is your outcome. Let's say, we want y to increase. It's something to do, some health thing. All right, so now there's 2 possible outcomes for each subject. You either have y of 1, that's your outcome had you taken the drug, you're in the treatment group, and y of 0 is your outcome where you're in the control group. Those are 2 things that you can sort of wrap your head around, right? But you can only observe one of them. However, if we're talking about causation, if I said, did being in the treatment group cause your outcome to increase, what we really want to do is compare those 2 things. Right? So what we really want to do is compute this y1 minus y0. So that's your outcome had you been in the treatment group versus your outcome had you been in the control group. We want to know what the difference is. If that's 0, then there was no difference. If that's huge, then the drug had a big effect, right? The problem, again, is we can only observe one of those. I can either give you the drug or not. I can't do both. I might design an experiment where I eventually give you both, but at one time I can only give you a single treatment. So you get a table like the one below, right? So for the 3 people that are in the control group, you observe y0. That's their outcome under control. For the 3 people in the control group, you observe y1. Now, for none of those people can you observe y1 minus y0 because one of them is always missing, right? So here... But this allows, so instead of looking at individual subjects, we can look at the population. So let's say that the causal effect of interest that I really, really want to get is I want to see whether or not the difference between your outcome when you get the treatment versus when you get the control, what it is averaged across the population. I'm calling this delta on this slide here. Okay, so that's delta. That's the average treatment effect. So that would be the combined difference between y1 and y0 for everyone in the population. That is a causal effect, right? That's basically saying, like, if we had 2 parallel universes, and I gave you the drug in one and the placebo in the other, and I took the difference between them and averaged them, that would be a causal effect. I think most of us can agree on this. We can argue about it, but to me, that's a tangible causal effect that that I'm interested in estimating, and that I can state, and we can argue about. Well, that would be great to argue about it, because it's arguing about something that's very tangible about causation, a statement about causation. However, I can't estimate it because I have all this missing data. You can look at the table. I can't estimate the average of those things. So what can I estimate from this? Well, let's be practical. I'm a practical guy. What I can estimate is I could take the average of everyone who's treated and use that as a proxy for y1, and then take the average of everyone who's untreated and use that as a proxy for y0. And I take the difference between them. But that's not the same thing, because then I'm computing something called D here, and that's the outcomes Y conditional on that you were in the treatment group versus the outcomes Y conditional you were in the control group. Now that's not the same thing as my causal effect. So what D does is it measures associations between the treatment and the outcome. What delta does is it measures a causal effect. Okay, so those are two different things. So I have a method that using the data, I can measure an association. But I have something delta that measures causation, which I can't get at because I don't have enough information. So what is the poor guy left to do? Well, I can start making assumptions in which D actually estimates delta. That I'm allowed to do. I can sort of try to get rid of those conditionings and whatnot. And that's sort of the key of statistical causal inference. Now, so again, D implies that they're associated. Delta implies that there's a cause. And so to equate these two terms, I need to make assumptions. And so basically what I need to say is that, well, you know what? I need to say that the missing Y1s for the first three people, the Y1s for subjects 4 to 6 are sort of representative of them. Right? So I could fill in the missing data using those guys, and vice versa. So basically, I have to kind of say that the subjects have to be exchangeable with respect to their treatment. So if those guys were in the treatment group and I'm in the control group, their response in the treatment group would be sort of indicative of what I would have had. Okay? So when is that true? Well, it's true when you randomize the treatment. And that's why randomization is such a good way of looking at treatment efficacy. Okay? So that's sort of I think a lot of people can sort of wrap their head around that in the sense that if I want to have causal effects and I want to see whether this drug is treated or not, I can't let people self-select to it. I can't say, well, this drug is going to work for me, so I want to be in the treatment group, and this drug is not going to work for me, so I'm going to be in the control group. Then you're obviously going to get a biased result, right? You need to randomize people. And that's what mathematically what we're saying here as well. So I think it makes sense if you think about it a while. Now, this sounds a little bit esoteric, but it turns out to be a very powerful framework. So my colleague Michael Sobel, who's an expert in this area, and I have written a series of papers about this, and we've shown things that modeling the bold signal without adjusting for systematic error can generate misleading inferences about causation, which is pretty natural. That if you use Granger causality, it can lead to erroneous inferences about sort of counterfactual causality. And we've given conditions under which you can use a structural equation model and make causal conclusions as well. So in keeping with sort of the framework that Moritz put up with mapping brain response to behavior, let's think about this, and let's think about this is a simple, very simple three-variable structural equation model. So you have a treatment, you have brain response, and you have some outcome, some behavioral outcome. And let's say that each subject receives one treatment. So you receive you receive a stressful stimuli or a control stimuli. You have brain response, and then you have some stress test or something like that. Okay. So we can model this using this, and we can estimate all these links between the different things using a structural equation model. But that only gives us association. That gives us that D, remember, that we had when I was playing around with that table. So this is only an association. We haven't even really talked about what causal effects that we're interested in. So let's say that we're interested in estimating the causal effect of M on Y. Okay? So what assumptions are needed for a causal interpretation of the link to M to Y? So using counterfactual notation, we can express that. And then we can look at what it is we're estimating from the SEM, and then we can make assumptions in the same way as we did in the silly little example I had, right? And so I'm going to avoid that just for clarity purposes. But it turns out that what we really need to know, it doesn't matter if you randomize the treatment. So if you randomize people to Z, to treatment and control group, it doesn't matter. You're still going to run into problems making causal links between the brain response and the outcome. And so among other assumptions, there's a lot of different assumptions, but one of the key ones is that there can be no unmeasured confounding between M and Y. Okay? So there can be no unmeasured confounding between M and Y. So when is that going to be violated? Well, let's just say that there happens to be people who their genes make them respond more highly to the brain in the brain. So you have a higher brain response versus people that don't have this gene or something like that. And you also happen to perform better on the test if you have this gene. That's a confounder. So then basically if you're comparing different brain responses and seeing how that affects the outcome, what you're basically doing is you're comparing people with this gene to people without this gene. And that's not really what you want. So basically what you're allowing people to do is to self-select based on their genotype to a certain brain response. And that negates any type of causation. Here's another example. I like this example because some colleagues from mine at Hopkins, they tried to make this sort of predictive algorithm for predicting ADHD from kids. And it turned out that at the end of the day, their algorithm did really, really well, but it wound up being a glorified sort of motion detector, right? Because the kids with ADHD moved a lot because, they had ADHD. So you could think of that head motion could cause your brain response to look higher than it is, but it could also cause you to be in the outcome group ADHD. So that's sort of a confounder that is really difficult to deal with. And so these type of unmeasured confounders, it's sort of easy for me to state that, we can't have that, but it's really hard to guard against that, right? So it's generally not possible to test for these things. You just sort of have to assume them. And that's fine to assume them, but I think that if we're making causal statements, we have to start saying that, this is causal under the assumption that we have no unmeasured confounding. And then, as serious scientists, we can discuss whether or not that's reasonable or not. And I think that's where the sort of the discussion has to be at, rather than just saying it's causal and cross your fingers behind your back, right? Basically, the key idea here is that when would M cause Y? Well, the most ideal thing would be if you could randomize your brain response, right? That would be a really terrific way to get at causation, and that's why I'm sort of excited about the last talk, because things like neurostimulation sounds really exciting to me about, to making causation about things like mediation and effective connectivity, because it allows you to randomize one step further down the pipeline. So you can randomize people into treatment and control groups, but then if you can randomize further down, it's going to sort of dramatically increase the power of causal statements that you can make, I believe. And so anytime we make even, simple causal statements, we have to be very careful about potential confounders, such as the one I mentioned. And so what are some ways around this? Well, I think that if you're going to base your study on causation, you can design your experiment to make these assumptions. So I just gave you one example of an experiment. I could design the experiment differently, and I would get different assumptions that need to hold for causation. So thinking about causation needs to occur in the experimental design if causation is your goal. Okay? So it's not like I'm going to take my study any which way and then hope I can make causal statements. It doesn't really work that easily. If you want defendable assumptions, you really need to incorporate that early on. You should try to control for characteristics that may differ systematically between the different treatment groups, such as the genetic information. Sometimes you have a lot of demographic information and whatnot. In statistics, we have something called propensity scores that allow to do efficient matching. So you can take high-dimensional things and match them using specific scores. And then finally, neurostimulation sounds, I'm very intrigued by that possibility as well. So just as a conclusion, in the last few decades, statistical causal inference has really taken off, and it formally expresses this idea that causal relationships sustain counterfactual conditional statements, so it uses this counterfactual type of causation. It allows us to define causal estimates of interest, so we can talk about whether or not it's a reasonable causal estimate, and it allows us to give conditions under which we can actually estimate causation. And, so it's just not enough to have a good data set. We also have to have certain assumptions that need hold, and they're above the assumptions that we have just for using, say, an SEM or something like that. And that's important to realize. So I want to thank my colleagues, Michael Sobel and Tor Wager, who've talked to me about this stuff, and NIH. Thanks.
Good morning. I'm waiting for the slides to come up. We've now heard already what we're interested in neuroimaging. That was Russ Poldrack's talk. And we've heard about the pitfalls and assumptions that we have to make if we go about causal inference. And this talk is about practical tools, like how can we actually obtain causal hypotheses, because they remain hypotheses. They're based on assumptions, and eventually we have to validate them to actually make them like to validate whether our hypothesis is true that is based on these assumptions. To motivate this example, we'll make clear where we're heading at. So here we have two brain maps. The top one is obtained from a decoding model, and the bottom one from an encoding model. What the group of Alexander Huth and the Gallon Lab in Berkeley has done is they've presented a 2-hour video of natural stimuli to the subject. And during this, they have recorded fMRI. So they have the voxel activity at each second, and at each second they have an annotated image that has been presented to the subject. So we know which person, object, or action has been taken place in each second of these videos, and we have the voxel activity. So the top plot shows the voxel weights if you train a decoding model that tries to predict, is person A in this image right now or is it not? So you feed in the voxel activity and you try to classify or predict, has the subject at this given time seen person A in the movie or not? And you will find certain regions blob up with high weights, certain other regions have a very low weight. In the bottom plot, you have the encoding model, which is basically you try to predict the voxel activity given you know what's shown in the movie. So you know person A is present in the movie, and you try to predict what's the voxel's activity. And what we will find is basically there's 4 different cases that can happen. A region can show up in both models, which is the orange blob here. It can show up only in the decoding model, only in the encoding model, or not show up in any of the models. And if we actually look at the data of this very experiment, we find that all 4 cases can actually occur in practice. Now the question is what to make out of this. We use decoding models, we use encoding models, we check which regions show up, but we find a mismatch between the two. And the idea of this talk is to actually explicate why there's very interesting information in this mismatch. So we can actually maybe use this information to get to causal hypotheses in the end. So if in decoding model, encoding model, we have a stimulus that is presented to the subject, and we're trying to get something out of this. So let's first start with the encoding model. An encoding model takes your label or your category, or is person A in the movie right now or not, as an input and tries to predict what is the voxel's activity at each given time point. So this might be modeled by a GLM, or you check for each voxel, is there a difference in means if I'm looking at the seconds where person A was in the movie versus the seconds where person A wasn't shown in the movie. And then you can check basically for each voxel, is it associated with the experimental condition? So if there's a big difference between means that is significant, then maybe this voxel is associated with person A showing up in the movie or not. The question is, what can we get out of this association? Because it's just association, not causation. For this, let me introduce Reichenbach's common cause principle that actually dates back 60 years. And the idea is you have 2 variables, in our case the stimulus and the voxel, and you find them to be associated, which you can do by checking your encoding model, which region shows up. And if this is true, so you have 2 variables that are associated, then the Reichenbach common cause principle says there's only and exactly 3 cases how this can happen. The first one is there might be another 3rd variable that influences both the stimulus and the voxel activity. Hence, voxel and stimulus will appear associated. The second option is the voxel activity drives the stimulus, or the other way around, the stimulus actually influences the voxel. We've already heard that randomization is a good thing to do, and here it turns out that it's very good to do, because if you randomize the stimulus, you can actually exclude the first 2 options, which means you end up with the conclusion the stimulus actually drives the activity in the voxel. If I had presented another movie to you, your voxel activity would be different in that voxel that you found in the encoding model. So we can actually go see our encoding model. If we've randomized our stimulus for this one subject, we can check the regions that appear relevant, they are actually effects of the stimulus. So during this talk, we will fill in a causal interpretation chart. So let's see how this looks like. We're considering only stimulus-based experiments for this talk. You can do the very same thing for response-based paradigms. And we're asking, for each voxel, is it relevant in an encoding model? or is it not relevant in the encoding model? And then we fill in the last column, the causal interpretation. And we've just seen if you randomize your stimulus and you find a region to show up in the encoding model, you can conclude actually it is an effect of S. So intervening on S, showing different stimuli to the subject will affect the activity in this voxel. If instead you found the voxel not to be showing up in the encoding model, you can't conclude that it is an effect, but vice versa, it's indeed not an effect. If it was an effect, it should show up in the encoding model. It didn't show up, so it is not an effect. So this is safe to do. It's good news. We can obtain something from just using an encoding model. But we had both models, encoding and decoding, and we found a mismatch between the two. So let's just check the decoding model. The decoding model works the other way around. You feed in the voxel activity. Let's say you have your 5,000 voxel activities, and you try to predict for each image, during that second, has the subject been presented a movie image where there was person A present or not. So you get out your label, yes or no, person A was there, or person A wasn't there. So you use a classifier, feed in voxel activity, and what you do then is you wonder which voxel's activity was actually very crucial to classify whether person A or B was present in the movie. So what we're asking here is, if I look at a voxel and I remove that voxel or like disturb it randomly, does it actually impair decoding performance? If this is true, then I would say, okay, then this voxel is actually quite important to be able to classify. And to make clear why this is different from the encoding model, I've just reformulated this. It's basically asking, is a voxel's activity still associated with the stimulus after you've already taken into account all the other voxels? So the difference is here you account for all the other voxels' activity, whereas in the encoding model you just check, is this voxel associated with the stimulus? So it's a somewhat different statement that you get out of a region showing up in the decoding model. So again, we go back to our causal interpretation chart. We add the decoding model, and again, a region can either show up or not show up in the decoding model. And we wonder, can we obtain some causal interpretation from this? We will see two counterexamples why it's not that easy. So it's not that good news for the decoding model. The first one, so what I'm showing here is a causal graph that we assume is true. So let's say the data is actually following this causal graph. The stimulus drives the activity in voxel A, but also there's another voxel, voxel B, that acts and influences the activity in voxel A. So you can think of voxel B being additive noise. So it kind of gets influenced by the stimulus and voxel B. The problem is, if you now look at the decoding model, you will find that you need both voxels to decode your stimulus. So if you're given voxel A already, then voxel B certainly helps you because you can get rid of the noise in predicting the stimulus. So voxel B will be important for the decoding model. And of course, if you have voxel B, voxel A, which is an effect of the stimulus, will also be important to decode the stimulus. So you will find both voxels to be important, although voxel B is not actually an effect of the stimulus. So this is why in this causal interpretation chart, we fill in an inconclusive at that point. Just for a region to show up in the decoding model doesn't really tell us anything. The second example is that effects may be missed. So here we have another potential graph that might be true. The stimulus drives activity in voxel A, and then the activity in voxel A drives the activity in voxel B. If we observe this and we check our decoding model, we will find voxel A is enough. Voxel A contains all the information that we need to decode the stimulus, so we don't need voxel B. So voxel B is not important in the decoding model, but if you look at this graph, it's certainly affected by the stimulus. So again, from a voxel not showing up in the decoding model, we cannot really conclude anything. So we fill in an inconclusive here. So we have good news for the encoding model, bad news for the decoding model, and the question is, are decoding models useful now? And yes, we argue, indeed, it's very useful to have both models at the same time, because you can get further insights if you look at your encoding model and your decoding model. So what happens is we go back to our interpretation chart, and now we consider both models at the same time, encoding and decoding. And then there are four possible cases. Either a voxel is important in both models, shows up in both models, only in one of the models, or in none of the models. And now we're checking all those four cases. What does it mean for the causal interpretation we can obtain from this? I will show two examples that it's actually useful and we get more out of this. The first one is this one again. We've seen this already. So we know that In the decoding model, we won't find voxel B to be important because voxel A already contains all the information. So voxel B is not important for decoding, but certainly it will show up in the encoding model. If you check mean difference between two different stimuli, voxel B will show a difference because it is actually affected by the stimulus. So having both the decoding and the encoding model actually allows you to make inference, which is voxel B is an indirect effect of the stimulus. And you can prove that this is the only possible solution for this to happen. For a feature to show up only in the encoding model but not in the decoding model, then it has to be an indirect effect. And this is a conclusion that is robust to hidden confounding, so this is quite nice. And we have a further positive news here, which is from this fact, we can conclude that we have an indirect effect of the stimulus. The second example is if we check this graph again, where both voxels are important for decoding. We previously said that this is a counterexample for decoding models being hard to interpret. But if we, in addition, look at the encoding model, we will find, voxel A is actually associated with the stimulus. So this tells us it is an effect. Whereas voxel B is only a feature that helps us for decoding. It provides context for the whole situation. So if we go back to our chart, this disentangles the meaning of features that are relevant in decoding. So the one that is relevant in both is an effect. The one that is only relevant for decoding but not for encoding, that has to be a feature that is providing context. You can think again of it being a noise variable. And if you find a feature not to show up in any of the models, well, then it's definitely not an effect of the stimulus. To wrap up, what we've seen is a simple causal interpretation chart. I've only shown it for the stimulus-based setting, but you can also obtain a similar chart for the response-based setting. And what you can do is you check the relevance in an encoding model, which basically checks for association, marginal correlation. So is the stimulus correlated with this voxel activity? And either this is true or this is not true. You can look at this, for example, when you have a GLM. Then the second thing is you can look at the relevance in a decoding model. So you train a classifier that tries to predict, given all voxels activity, whether person A shows up in the movie or not. This is basically checking, like taking into account all the other voxels, is there remaining association between your stimulus and your voxel's activity? And you can again, either this is true or this is not true. And if you have this, you can just go, check the interpretation chart and read off the causal interpretation. If there is a causal interpretation, it will say so. If not, it will say inconclusive. We cannot say anything. We've extended this work because now the first part actually was about inferring how a voxel's activity relates to outside stimuli or responses, if you consider response-based paradigms. So how voxels give rise to movements or something. Maybe we're also interested in establishing cause-effect relationships within the brain, between voxels, which you can do in stimulus-based settings by the so-called STI algorithm. And what this does, it allows you to infer certain cause-effect relationships between neural processes. For this, you can download the code, feed in your data, and check whether you can find the statistical properties that allow you to infer, between voxel A and voxel B, there is this certain cause-effect relationship. And again, to stress this fact, this is robust to hidden confounding. So the chart on top and this causal inference algorithm, if you have hidden confounding between the voxels, that doesn't really matter. Then we'll refrain from a conclusion. But of course, there are caveats. We already heard that there are always assumptions. So there is no inference without assumptions. This is why we need to validate our causal hypotheses. We rely on, crucially, on one assumption that is called faithfulness. And what that basically means is if the stimulus causes activity in a certain voxel, then we will observe that there is an association. So nature isn't hiding that dependence. Otherwise, that would mean there can be a causal link, but we don't see them to be dependent in any way. So this kind of nature hides these dependencies. We have to assume that this is not the case. And the second thing is we need to be ready to interpret negative results, non-association, uncorrelatedness, being not relevant in a decoding or encoding model, which is something we actually commonly do. If we say, for example, a certain region is task-specific, we're implicitly saying the regions around are not task-specific, although maybe we're just not able to establish this relationship. I want to point out 2 papers, which is the second one in this list is the causal interpretation chart, and the third one is the extension where we've tried to establish cause-effect relationships within the brain. And then there's further extensions where we're currently working on extending this framework to obtain patterns, whole patterns or linear combinations of features that have a certain cause-effect relationship. And with this, I want to thank you for your attention.
Good morning. My name is Christoph Herrmann, and I would like to talk to you about how transcranial brain stimulation can actually show a causal relation between a physiological process and a cognitive process. And I will briefly introduce the method to you. It's called transcranial alternating current stimulation, or TACS, and then I'll show 2 examples on how we do that. So here you basically see the principle of what we're doing. We have a subject sitting in a lab setup doing a cognitive task. And while the subject is doing the task, we attach 2 electrodes or more on the scalp, and we run a current through the scalp. And we're trying to, by this way, modulate a physiological process and hope that in turn we can modulate cognition, perception, what have you. And in our case, we record EEG to demonstrate that we're actually modulating a cognitive process, but I could imagine many of you would rather record fMRI. And I should mention there are at least 2 very nice posters that actually demonstrate that TACS can modulate fMRI parameters. So the current that we're running through the brain looks like a sine wave. There can be many other current forms like a DC or an impulse or anything else, but we're trying to explicitly modulate the sinusoidal brain oscillations, and therefore we're using sine waves, and that's why it's called TACS, transcranial alternating current stimulation. One thing that we need to know is if we attach the electrodes at specific locations on the head, where in the brain would you actually find current flow? We do this with finite element simulations, so we have a brain model derived from MRI that mathematicians used for us in order to predict the current flow. And you can see with the large electrodes that we used in the studies that I'll show here, it's not very specific, but the current flow is stronger in the vicinity of the electrodes than further away. Meanwhile, with smaller electrodes, we can be much more spatially specific, I should say. And just to demonstrate that this actually works, I would like to point out one animal study that has been done where Flavio Fröhlich at the same time recorded spikes intracranially and applied sine waves of different frequency to the same patch of cortex. And what you see in the black trace is the intrinsic oscillation of this piece of brain tissue. And then the 3 colorful traces show you what happens if you apply different frequencies of sinusoidal currents. And you can see that the sine waves order the spiking and influence the interburst frequency. So what we believe happens is something that is called entrainment. The brain synchronizes to the sine wave that you are applying. The important thing that you should see is the sine wave is actually doing something to the brain oscillation, so the sine wave modulates the physiological process. And with that, I come to the first experiment that I want to demonstrate, the first hypothesis that we want to evaluate with TACS, and it's based on a theoretical concept. For hundreds of years, psychologists have believed that there is a lot of randomness in our perception and action. So, for example, if I stimulate the very same stimulus to you 100 times, and it's a near-threshold stimulus, you will have 100 different reaction times. Sometimes you'll see it, sometimes you'll not see it. And I don't believe in randomness. I believe in a mechanistical explanation and in processes that we don't understand so far. And my favorite explanation is the brain oscillations. And if you look at this slide, you will see that this is one assumption that has been used in many studies that show that the phase of brain oscillations are important for perception. If you have a brief stimulus and you present it in the hyperpolarized phase of an oscillation, like in the right diagram, this may not lead to neural firing and this may not lead to conscious perception. And in the left, you see the same stimulus, but being presented during a different brain state. You're in the excitatory phase of an otherwise subthreshold brain oscillation, and in this case, the brief stimulus does lead to neural firing and does lead to conscious perception. And we're trying to demonstrate that this is actually happening by applying such a sine wave from the outside, at the same time with a sensory stimulus. So here you see the setup. We are evoking or inducing the oscillation from the outside. That's the sine wave that you see in A. And then we are delivering auditory stimuli in specific phases of this oscillation. And the task of the subject is shown in B. You will always get indicated by a letter in which phase of the experiment you are, 1 or 2, and you as a subject have to say whether the 4 click sounds are presented during the first or the second phase. So if you look at the first trial interval, it's clearly that you can see that the 4 clicks are presented during first phase. During the second phase, there's nothing. Then the white letters indicate that you're supposed to respond, and if you did that right, you get green feedback. In the second trial, you can see the 4 clicks are presented during the second phase of this trial, and you see that the response was wrong. And the interesting thing is, if we now apply bilaterally TACS at 4 hertz, let's not talk about all the parameters, at the same time as we present the auditory tones, then we can manipulate from the outside whether the tone is in a specific phase of the oscillation or in another phase. And this leads to a specific behavior that depends on the phase of the oscillation, as shown in A. The gray curve is a sine wave, a 4 hertz sine wave, and the black trace is the mean of the subjects. Some of them you can see in B, and you can see, yes, it does follow the predicted wave shape, and in C you can see the difference between the positive half wave and the negative half wave. And as we heard before, we have to compare that to a sham group that received placebo stimulation. That is no stimulation. We pretend we stimulate the group, but we don't, and we see there is a significant difference. So yes, we think we can, with TACS in the first step, modulate the brain oscillation, and then we see how this manipulation has an effect on perception. And I brought a second experiment with me, and this actually is based on something that Christoph Michel found long ago. Is he here? He's one of our local organizers. They showed that if you have to do a mental rotation task, this depends on the amount of alpha desynchronization that you see during the trials. And another finding is that if there is high alpha amplitude to start with in the baseline, then there's also a strong desynchronization afterwards. So taking these two together is again something that you can test with TACS. If we apply TACS at the individual alpha frequency, we have shown in other studies, this increases the amplitude of the alpha activity. So with these two findings, this should help mental rotation. So we stimulated the back of the head of subjects. The stimulation electrodes were attached to CZ and OZ because the strongest current flow is in between the two electrodes where the alpha generators reside. And we've shown in other studies this does elevate the alpha amplitude, and at the same time the subjects are doing a mental rotation task where they have to say whether or not two rotated figures are the same. In the bottom example, the rotation angle is 0 degrees. There you see nicely that the two are the same. And at first, if you look at the top left, you see the difference of the increase in the subjects from before to after stimulation. The stimulation has a bigger increase than the sham group that we again investigated. And if you want to look at the event-related alpha synchronization, that's shown in the top right diagram. So 0 is the onset of the figures that you have to rotate, and on the horizontal axis you have time, on the vertical axis you have frequency, and the blue is the reduction of alpha amplitude after stimulation of the stimuli. And in the lower left, you see that we were able to increase the alpha before stimulation, and in the lower right, you see that this in turn modulates how much the alpha goes down. So we think the difference that we see in performance is related to this difference in increasing alpha and thereby increasing the decrease. So we think these are two examples that demonstrate such a causal link, and the take-home message is that if you apply this or other simulation techniques, in our case at a specific frequency that is tuned to an oscillation of which we believe it's relevant for some cognitive process, then you are able to demonstrate a link between such a brain oscillation and a cognitive process. And we think it's important to combine TACS with some physiological measure. In our case, it's EEG, it could be MEG, fMRI, what have you, in order to demonstrate that in the first step you are modulating a physiological process, and in the second step this is actually having an influence on cognition. And we think that this is potentially applicable in future in so-called oscillopathies, so where diseases where one of the main symptoms that you see is a changed brain oscillation, like in ADHD and schizophrenia. And with that, I would like to thank you for your attention and my group for the nice work. And now we're all happy to take your questions.
So we have a 10-minute discussion. So if you have questions to any of the speakers, please come up to one of the microphones. So, Gabi.
Yeah, my question is, there a couple of years ago, lots of other, or at least two other techniques were introduced, dynamic causal modeling and Granger causality. So both of them have causal in their title. Can you comment on those?
So who of you would like to comment? Martin?
Well, having causal in the title isn't a necessary condition for causality, I'd say. But
sufficient?
It's sufficient. I mean, sorry, I'm a little tired here. So it's not as sufficient. But I mean, to me, I mean, those methods, can be used in their own right. But I still think that if you want to make truly causal statements of the type that I've been mentioning, you need to still go beyond that and make additional assumptions, and that's where I think is sort of the shortcoming is we haven't gone beyond just the assumptions of the methods, but we also need to go to lay on assumptions needed for making causal statements of the type that I'm mentioning.
Okay, so a question over here.
Hi, Sebastian. So in the big table with the ticks and crosses that you have, for the column corresponding to the decoder, whether it's tick or cross, doesn't it depend on the choice of the classifier you use? I can imagine with different classifiers, the tick and the crosses will be different, right? So how does that fit into your framework then?
It definitely depends on the classifier. That's quite right. I think that makes the problem even more problematic. So the results I've shown is if your decoder does exactly that statistical test that we think it does, so if it's like perfect in that sense, right, even then you cannot conclude anything. If you then add the variability that you have for different classifiers, it makes it even worse. You cannot even say whether this blob is associated in this certain sense.
Can I ask a quick second question?
Yes.
And so then to determine whether, so let's say you have the perfect classifier, which we don't have, but let's say we have it, to determine whether it's associated with the decoding or not, you mentioned something about if you remove the voxel, whether it affects the accuracy. So do you mean you just look at, for example, the SVM weight on the voxel, or do you mean you remove the voxel and retrain the SVM on the entire data again to see if the accuracy actually decreases?
There's many ways to decide whether voxel is relevant for decoding. We usually randomize one voxel and check whether it decreases performance significantly. You can either retrain, which makes it obviously more difficult because then you have a simpler model, which might counterbalance the effect of decrease because you've removed a voxel, but increase because you've got a simpler model. So this is based on you have the statistical test that actually works.
So maybe I may add something very brief to that. I think people often ask me, so does causal inference actually work? And I think people mean very different things by does it work. If people mean it gives you a correct result all of the time, or a p-value for each individual decision, whether you're correct or not, then no, I don't think it works yet. But if you say it works if you're better than chance level at inferring causal relations, then yes, we have good evidence that it actually does. So there's one more question back there.
I think, yeah, my question was related. I think it's a similar question, and how much the table would depend on the choice of the regularization of the classifier. And I think maybe it's probably the same answer as before, because great talk, actually, Sebastian. I really enjoyed, but yeah, I was wondering how much, I think is you already, I don't know if you want to add something, but I think, yeah, it's the same question as before.
Well, if I can add one thing, that is, encoding and decoding models are actually just one particular type of statistical test. So there is PC algorithms or FCI algorithms in causality research that actually test for all conditional independencies and all pairwise marginal dependencies. And if you were to do this, you could get more causal insights from this. So this work was basically to show encoding model, which is a marginal dependence test, and decoding model, which is you condition on all the other voxels and check whether a voxel is still relevant. That already allows you to get some insights. So actually, I think we should move beyond decoding models and do the conditional independence tests. The caveat here is these are very difficult to implement. So the actual statistical test for conditional independence is really difficult. So I'd say, yes, it depends heavily on the classifier, but this is showing even if you were to do the perfect test, you get wrong results if you interpret them without paying too much attention on the details.
So I think the next question is over there.
I have a question to TACS. My question is about peripheral effects. The retina and the vestibular system, but also the hearing system peripherally is very sensitive to oscillations. So how much do we need to kind of test for the peripheral effects when we look at perception?
Yeah, that's a very good point. It has been shown that if you apply TACS, then you see a slight flickering sensation in the periphery of the visual field. And of course, then the effect that you're looking at could be by this flicker. And therefore, I didn't mention all these details. We're recording a certain threshold. So one threshold is whether or not the subjects perceive a flicker, and we stay below that threshold. And another is a tickling sensation under the skin. And again, if you can feel whether you are in the simulation group or in the sham group, this could, of course, modulate the perception. And therefore, we also stay below that threshold.
But does this exclude subliminal effects?
Hello. Hi. I have a question, really for Sebastian, but anybody could comment, I think. And the question is about what happens if you consider different levels of noise in different voxels when you're trying to estimate causal relationships between stimulus and voxel 1 and voxel 2. And I think that that's going to be really problematic. And I think it relates to your assumption of faithfulness, that you have to make some assumptions about there being no noise or equal noise levels across all measurements.
Maybe I can take the question. So we design all our methods in a way that they are conservative. If there's too much measurement noise, our methods will say we can't say anything. And they will only say there is a causal relation if the noise has been small enough to actually detect the causal relation. And I think it's very important that you design methods in this conservative way, that you only decide if you have sufficient evidence. Yeah, I think over there's the next question.
On the TACS, I'm curious to know what range of frequencies you've explored. So you talked about 4 hertz and 10 hertz, but what about infraslow and maybe faster?
The slowest we have gone to is delta, as we showed, but we've also looked at theta, and the fastest we looked at was 40 hertz so far. We always try to look at the literature and to see was there a correlation in the past between a brain oscillation and a cognitive process, and then we took this oscillation and tried to target a parameter of this oscillation. Sometimes it was the amplitude, sometimes the frequency, sometimes the coherence between the two hemispheres, but so far it was between 4 and 40 hertz.
Okay, are there any further questions? If that is not the case, oh, one more question, yes.
Hi, I have a question to Russell, because you said that we give different weights to different ontologies in your modeling. So my question is that whether it's a decision of a researcher or you somehow model it, or it depends on the number of studies in your database. How do you give different weights to different ontologies when you try to predict the outcome on a certain task in your database?
It's all based on the interpretation of the set of people who sat down to try to do the annotation. And that's a fundamental problem. I mean, ultimately, we'd like to have, probably there's going to be different ontologies from different groups. Certainly, when people disagree about sort of, what the conceptual structure is, they're probably going to put together a different ontology. And that's where we'd like to be able to actually test those against one another. But the analyses we've done so far, it's basically just we sat down and wrote down an ontology and, that was our interpretation of these particular sets of tests. So it's all, everything that I showed is conditionalized on that particular ontology. That's currently a limitation of the work.
Okay, thank you.
So our time is up. Thank you, everybody, for attending our symposium. It was great fun. And we now have a 15-minute break before the next keynote lecture starts here.